to the online lecture series on power electronics. Our today's lecture is the dead time generation between two complementary waveforms. We have talked about the importance of generation of dead time between two complementary waveforms a number of times, and some groups have also generated this dead time in the lab, and we know the importance of this dead time and why do we need the dead time between two complementary waveforms, especially in the case of half H bridge and full H bridge. Today we will be discussing the calculations using which we can generate dead time between two complementary waveforms. Suppose you are given with this condition that generate complementary square waves with a dead time of 2 microsecond and a frequency of 20 kilohertz, and the duty cycle ratio that you need to achieve is 40/60. This value of dead time, this will come from the calculations of the observing the dynamics of the switch in lab. So once we know the maximum dead time of the two switches from the half bridge, then on the basis of that the maximum value of the dead time will be considered, and that will be our value, and this is the frequency at which we want to do the switching of these switches, and this is the duty cycle on the basis of which you want to operate the switches in a particular ratio. It may be 50/50, it may be 40/40, or whatever you want to do. So the first step is to calculate the new time period. This was our sampling frequency or switching frequency, 20 kilohertz, and the time period corresponding to this time is 50 microsecond. So I needed to generate a dead time of 2 microsecond. Therefore 50 microsecond minus 2 into 2 microsecond. This 2 has been introduced because I want to introduce this much gap, this much dead band or dead time at the starting of the wave as well as at the end of the wave. If this is my first wave and this is my second waveform, so I want to introduce a 2 microsecond dead time in this region and another 2 microsecond dead time at this stage. So that's why I have multiplied this by value of 2. Now the second step is to calculate the on time of each wave of both of the complementary waveforms. If I call one of this waveform as signal A and the other one as signal B, so this is my new time period that has been that I am left with after cutting off that dead time. So this is 0.4 and 0.6. So these are corresponding time periods for which this particular signal will be on. If I want to divide them in ratio 50/50, in that case these values will be replaced with that particular ratio. So these are the new time periods corresponding to the time period 46 microsecond that I am left with after subtracting the dead time from the total time period, which was 50 microsecond. So the next step is to calculate the duty cycle based on time, and new time period. These values, the one I calculated in my previous slide, these are basically the new time periods corresponding to 46 microsecond. But I cannot change this value 50 microsecond these values, they came from the uh, time period 46 microsecond. I want to find the ratio of these new time period corresponding to the original time period, which was 50 microsecond. So with that, the duty cycle is 36.8% and the duty cycle of B waveform is 55.2%. So the 40% time cycle has been now shifted to this value 36.8, and the 60, the waveform which supposed to be at 60% has now been has been now reduced to this new value 55.2%. And the last step is to introduce a phase shift in any one of the waveforms. Either I can introduce this phase shift in the waveform A or either in waveform B. So what I am going to do, I am going to introduce the phase shift in the B signal. So its time period, which was 27.6 microsecond plus 2 microsecond divided by 50 and multiplied with the complete 360 degree. So this is the phase shift that I will introduce into the this waveform B. And alternatively, I can also introduce the phase shift in A waveform by using its time period. So I have to only introduce phase shift in one of these signals. I am keeping one of the waveforms in its fixed position and sliding the next one over it, so that I can achieve a waveform like this, in which I get a dead time of 2 microsecond on both sides, on this side and on this side as well. So you see what will happen if I do not cater this time period, and I directly calculate the time period corresponding to this value 27.6 divided by 50 microsecond into 360. So then we will get some other angle. That is basically the same calculations that we did in case when we were not introducing any phase any dead time in our complementary waveforms. But now when we are introducing this dead time in our circuit in these waveforms, in that case I have basically slided this value onto one side. Otherwise, what would have happened is that the whole of this dead time would have been only to have been shifted to only one side. For example, on one side there would have been no dead time. For example, see this point. In this, both of these will coincide. The whole of the dead time will be on this one side, and this will be 4 microsecond instead of 2 microsecond. So what I have tried to do is to introduce a phase shift in it by delaying it further 2 microsecond. Instead of introducing the waveform the phase difference, the dead time on one side, I will slide this waveform a bit forward. And how much is that? It is by this time period 2 microsecond. So now the waveform that I will get will be of this kind. This is the case that I am talking about. If I do not add this value of 2 microsecond, and in your case this value be whatever the dead time you want to introduce. So you see that these waveforms, they are coinciding on one end, and we have introduced the dead time of dead time, but the whole of the dead time is being shifted on